So now we turn to this question. What can be done to increase the speed of electrical conduction down the length of a neuron? In other words, if I start with my action potentials at the axon helix, and those action potentials come down the axon to the end, is there anything that can be done to increase the speed of that action potential travel from point A to point B? Or another way to think about it is to decrease the time elapsed from point A to point B. Can I make it quicker? Can I make the electrical conduction faster? And the answer is yes. In the animal kingdom, there are kind of two different solutions to that potential problem. And it is a problem. If you are an animal that has slow electrical conduction, your behaviors are going to be equivalent to the sloth from Zootopia. And if you haven't seen that movie, it's pretty funny. I encourage you to watch it if you have the time. But if you're not sure what I'm referring to, just Google sloth Zootopia and you'll see what I mean. In other words, we need to be able to respond quickly to changes to our environment. And that means that we need to have fast electrical conduction through our neural network. And that means that going from point A to point B in each neuron needs to be as quick as possible. So what are the two solutions? One solution is to take the diameter of the axon and make it bigger. Now, I don't want you to write this down if you're in my class because I will never test you on this. But making a larger diameter axon, think of it like a thin copper wire that you're now making much thicker, is going to improve the speed of electrical conduction. I'm not going to get into the physics of why that is, but it is pretty well known if you're familiar with electromagnetics and electrical circuits. Having a larger diameter wire decreases the resistance and therefore increases the flow of ions. That's basically it. Many invertebrates employ this technique and create what are known as giant axons. And by giant, I mean 1 millimeter in diameter, which probably doesn't seem very giant at all. But maybe it would help if we had a point of comparison. While giant squid, for instance, have a 1.5 millimeter diameter axon, human axons are going to be in the micrometers, so much, 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 much smaller. Okay, we simply do not have enough anatomical space in our bodies to allow for the number of giant axons that would be needed for fast electrical propagation through all of our tracts. So instead, most animals have evolved to have a different solution, and that solution is myelination. So myelination can be thought of as a rubber coating around an electrical wire. It helps preserve the charge and therefore makes the action potentials that do occur between point A and point B much more efficient, and it increases the speed of transmission. This is sometimes referred to as saltatory conduction, and perhaps you've learned about it in anatomy. So I'm going to give you a very brief analogy or a kind of a simplified example of why myelinated axons propagate electrical signals so much faster. In an unmyelinated axon, all of the axon is going to participate in action potentials. So we could think about the propagation like this: action potential, action potential, action potential, action potential. Right? And so all of these are going action potentials all the way down. In a myelinated axon, action potentials only occur at the nodes of Ranvier, the spaces in between the myelin sheathing. And just as a quick recap, in a previous lecture we learned that myelin sheathing is caused by glial cells. In the central nervous system, it's the oligodendrocytes that create the myelin sheath, and in the peripheral nervous system, it's Schwann cells. But the point being that the action potentials only occur in those little spaces that are called nodes of Ranvier. So this means there are fewer action potentials that happen. So the electrical signal instead does something like this. An action potential, an action potential, and it actually moves through a lot faster. Saltatory conduction is sometimes referred to because it almost looks like you're shorting the circuit. You're jumping from node to node to node. Now, in a classroom, I will actually demonstrate this. I've tried to do it in my house. I really don't have as much room as I would in a classroom, but let me go ahead and demonstrate the difference in terms of time for an unmyelinated axon versus a myelinated axon. Okay, so the benefit of the myelinated axon is that it improves the speed of electrical conduction by about tenfold compared to an unmyelinated axon of the same length. And another benefit is that because you have fewer action potentials occurring, because they only occur in the nodes of Ranvier, and we'll get into the mechanisms of that momentarily, but because action potentials only occur in nodes of Ranvier, it's actually a lot more energetically efficient to run a myelinated axon compared to an unmyelinated axon. And that might seem a little weird. What do you mean it's more energetically efficient? Well, action potentials are not free. Every time you have voltage-sensitive sodium gates and potassium gates opening and closing, you let in sodium and you let out potassium. Well, that chemical gradient has to be restored by the sodium-potassium pump. So the more action potentials you're running, the more the sodium-potassium pump has to churn in order to restore the gradient. So if you have fewer action potentials, you have less cleanup, and therefore you spend less money. So let's go ahead and list both of these benefits of myelination. Okay, make sure you pause the video and go ahead and write these two benefits down. The benefit that we're really going to focus on is going to be faster electrical conduction. That's really our major focus for this lecture. So I've already said that fewer action potentials occur in a myelinated axon and that they only occur at the nodes of Ranvier. Now we're going to take a look at why this is the case. In order for an action potential to occur, we need to first open a voltage-sensitive sodium gate and allow sodium to move from the extracellular fluid into the cell. That can't happen in a myelinated area. So in this image here, you can see that at the nodes of Ranvier, those are going to be the only places where the membrane is exposed directly to that extracellular fluid and therefore is a viable place for sodium to find its way in through a voltage-sensitive gate. So the nodes of Ranvier are really the only places where any sort of ion movement occurs, and therefore they are also the only places where action potentials happen. Remember that this myelinated sheath here, this myelin, is all lipids. And so ions do not like lipids and don't want to have anything to do with them. So it turns out that myelinating the axon gives another benefit as well. When positive charge comes in through a node of Ranvier, it needs to rapidly and consistently make it over to the next node with sufficient strength. In other words, it can't have leaked out somewhere. With sufficient strength to depolarize the membrane over here and start the next action potential. And the myelin sheath achieves both of those goals. It not only preserves the charge, again, much like coating a wire in rubber helps preserve charge and prevents leakage, but the charge rapidly moves through. So it doesn't just dalliance. It doesn't like take its sweet time going la 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 la. It's like no, zoom over here. So let's address both of those. why does the charge zoom over to the other side? Well, you can think of this like a tunnel. I mean, the myelin sheathing is actually three-dimensional, right? So it's covering all of this. It's creating a tunnel there. And it's a tunnel of lipids. And the ions hate lipids and lipids hate ions. So you know what? When you're in an environment that you hate, you want to get out of there as soon as possible. And so in that way, when the positive charge starts moving into this tunnel, it's not going to be like, oh, I love you, enemy. Let me spend all this time with you, enemy. It's like, oh my gosh, I hate it. This is unfriendly, and I just want to get to the other side. Moreover, that charge is preserved, so there's not a lot of leakage. Electrical current can in fact leak, but the myelin doesn't really give it opportunities to leak. Now, how would it leak? The sodium-potassium pump is the most obvious way to kick any sodium that's there back out. And there probably are sodium, in fact, I know there are sodium-potassium pumps at the nodes of Ranvier. But the sodium-potassium pumps would not be able to kick out any sodium in the myelinated areas, because where's it going to kick the sodium out to? To a lipid layer? And where's it going to find that potassium that it needs to bring back in? So the sodium-potassium pump will not work in a myelinated area, and therefore the charge is preserved. So let's go ahead and write this information down. Now, I write action potential so often that I will often just use AP as an abbreviation for action potentials. So I went ahead and drew up my own node of Ranvier. And in this diagram, you can see what is happening. We've got our voltage-sensitive sodium gates and our potassium gates, as well as the sodium-potassium pump. But once again, action potentials can only occur at these nodes because this is where the sodium has good access to this membrane. Over here, how's it going to get through all that myelin? It's not. So no action potentials are going to occur in the myelinated area. Researchers have done some interesting studies where they've been able to show exactly where the gated channels are, and they are in fact localized at the nodes. And there really are no gated channels in this section of membrane over here. So only the nodes of Ranvier will facilitate action potentials. Now, there are a number of diseases out there that are called demyelinating diseases. Demyelinating diseases can be debilitating at best and fatal at worst. There are a number of demyelinating diseases where the myelin sheathing experiences some sort of destruction, thinning, or is just outright removed. And the outcome of a demyelinating disease is that the action potential propagation will usually either be much slower or may be completely blocked. In other words, it fails at some point through that axon. And you can kind of see why that might be the case here. Remember, the concept of myelination is predicated on this idea that when the positive charge comes in, it will be preserved and rapidly moved through to the other side. But if the myelin is missing, then sodium-potassium pumps will start kicking that sodium out because the extracellular fluid is right there. And therefore, we have current leakage or charge leakage. And by the time maybe even a little bit of sodium gets over here, it's not enough. We haven't reached the -55 threshold to trigger a subsequent action potential. And so no action potential occurs where the next node is. Multiple sclerosis is perhaps the most famous demyelinating disease, so I'll briefly talk about that. So multiple sclerosis is an autoimmune disease, and therefore your immune system attacks the myelin sheathing created by oligodendrocytes in the central nervous system. And so as a consequence, the neural pathways are disrupted. Now, what do I mean by a neural pathway? Neurons form networks where one neuron conveys information to another neuron, etc. And if we have electrical failure or failure of electrical conduction, then you might have successful electrical conduction down one, but then maybe it gets blocked right there, never makes it to its destination. This can result in impaired motor function, impaired thought, impaired speech, impaired, any of the pathways can be impaired. And so typically the first stages of multiple sclerosis are such where you have a demyelinating event that results in some sort of disability. Then you have some sort of recovery. So what's going on in the recovery? Well, it turns out that you have progenitor cells, stem cells, oligodendrocyte stem cells that will try to kind of repair the areas that are degraded. And by remyelinating them, you'll restore mostly the electrical conduction. But notice that it doesn't seem to be a permanent fix. Now, why it's not a permanent fix is unknown. But eventually, you'll get another event where you have an additional demyelinating event. It's usually somewhat localized. And then you'll have recovery, but it won't be full. And then something really interesting happens. If you have a neuron that is not conducting electricity reliably, so let's say that action potentials still happen to at this point, but there's too much loss of myelination at that point, and the action potential never goes any farther, the neuron itself will atrophy and die. And so you actually get neural degradation and death in later stages of multiple sclerosis. And that can't be solved by simply rewrapping new myelin sheath because there's no functioning neuron to wrap up. So it turns out that much like our muscle tissue, which can hypertrophy, which means expand the muscle mass, or atrophy, which means you lose muscle mass in response to use, our neurons seem to be somewhat plastic like that as well, where when neurons are getting used a lot, then they stay healthy, and when they stop being used or they're no longer functioning, they die off. So this covers one type of demyelinating disease. Another one that I'll just briefly mention here is called adrenoleukodystrophy, which gets the abbreviation ALD. ALD is very rare, and it usually is diagnosed in young boys. And it's usually fatal, also in adolescence. ALD is a pretty devastating disease. And if you're interested, I encourage you to go ahead and just Google adrenoleukodystrophy or ALD. And another thing that you can put in is Lorenzo's oil. So it's an interesting movie that is based on a true story of two parents who had a single son that was diagnosed with ALD, and it's a death sentence, as of right now, it really still is a death sentence, but they didn't want to lose him, and so they basically investigated the metabolic things that were occurring that caused the demyelination and came up with a really clever way to try to slow that demyelination. So it was a really interesting story about two non-scientists basically learning all about the known science to try to come up with their own cure. And Lorenzo ended up living until he was 30 years of age, where he was expected to die probably before the age of 10. Currently, there is some research going on with gene therapy that they're trying to fix. It's a genetic mutation. They're trying to fix the gene itself that causes the demyelination in the first place. So multiple sclerosis is not the only type of demyelination. There are a number of other diseases that also cause demyelination. But when you lose reliable propagation of electrical signals down the length of an axon that is supposed to be myelinated, but no longer is thoroughly myelinated, then the neural network is impaired. And then, of course, the consequences are failure to move correctly, failure to respond to stimuli, etc. All right, so that concludes this lecture. In our next lecture, we're going to take a look at the axon terminals and what happens when the electrical signal gets to the axon terminals. What happens next? I'll see you then.